What if you could perfectly simulate every single possible future? Just imagine seeing all the outcomes, every choice laid out, and then just, picking the best one.
It sounds like pure science fiction, doesn't it?
Totally. Like the Kwisatz Haderach from Dune.
Yeah.
That kind of superhuman foresight.
Exactly. But that very idea, that sci-fi concept, is actually fueling some really exciting and, frankly, pretty hotly debated work in AI right now.
Right. We hear a lot about large language models, LLMs, predicting the next word.
They're amazing at that.
But this is different. You're talking about world models, simulating the next world.
That's the goal.
Yeah.
It's a massive leap, right?
Yeah.
From just one word to an entire evolving environment, all its complexity.
Okay, so that's our mission today. For you listening, and for us too. We're going to dive deep into this whole world model field. It's emerging, it's complex, people disagree on stuff.
A lot of it, yeah.
Our goal is to sort of cut through that, pull out the key nuggets, help you wrap your head around what a world model actually is, how people are trying to build them, what you'd even do with one.
And how you'd know if it's any good, how to evaluate it.
Exactly. So you can walk away feeling informed, maybe learn some surprising things along the way.
And we'll definitely touch on some pretty sharp critiques of the current approaches. Plus, there's this new proposed architecture we should talk about, aiming for a truly general-purpose model.
Sounds fascinating. Okay, let's jump in. Simulating futures. It's not just Dune anymore.
No, it's becoming real science. That idea of seeing all the paths, that's really the core inspiration. But the question is, how do you even start building something like that?
Where do you draw inspiration from?
Well, from us, really. Human intelligence. Think about it. We have this whole range of skills. Basic body control, reading, sure, but also really abstract stuff. Planning, strategy, imagining what if.
And we do it all with the same brain, basically.
Seems like it, yeah. The same cognitive architecture handles it all, which is, quite different from your standard chatbot that's just focused on language.
So define it for us then. What is a world model, operationally?
Okay, at its heart, it's a generative model. Its job is to simulate possibilities. And not just in one type of scenario, but across loads of different domains. Physical worlds, social interactions, mental states, even evolution.
How does it work? Like mechanically?
That's pretty neat, actually. You give it the state of the world right now, let's call it S. And you give it an action, an agent might call it A.
Okay, state and action.
And the world model predicts the next world state, S, what happens after that action. Essentially, it's trying to predict the universe's response.
The universe's response. I like that. And this lets machines do thought experiments like we do.
Exactly. That's a term from psychology, hypothetical thinking. So you see someone crying, you might think, okay, if I go over, maybe they'll feel better, or maybe it'll be awkward, or maybe I'll help, but it'll drain me.
You run the simulations in your head.
Right. A world model gives a machine that ability to internally simulate outcomes before it commits to an action.
And this is where it gets really powerful, right? This idea of transferring knowledge to new situations.
Absolutely critical. The paper gives some great examples, like knowing how to scuba dive. That low-gravity experience might actually help you figure out how to walk on the moon. It's not identical, but there's transferable understanding there.
Or a mountaineer predicting terrain.
Could be incredibly useful if they suddenly needed to plan, say, a mountain ambush. Same core skill, different context. Or a really good gamer becoming a skilled drone pilot.
That makes sense. It's that underlying understanding of dynamics.
Precisely. And this leads to what we call zero-shot capabilities. Being able to perform well in situations you've literally never trained for.
Why is that so crucial? Why not just train for every situation?
Because you can't. Think about the real world. Landing on Mars, a robot navigating with sensors that are, constantly giving noisy or incomplete data. You don't have perfect access to the true state of the world.
So you need something to fill in the gaps, to predict.
Exactly. The world model becomes your best guess, your simulation of how things will likely unfold. It's critical for predicting that universe's response when reality itself is fuzzy.
And the potential applications seem huge. You mentioned physical, mental, social.
Oh, yeah. A truly general-purpose WM could simulate almost anything. Physics, like how water pours. Embodied stuff like balance, maybe even pain. Emotions, social dynamics, what's that other person thinking? Abstract planning, logistics, tactics, what-ifs, scenarios, counterfactuals, even potentially long-term evolutionary processes.
How does this simulative reasoning stack up against older AI approaches, like logic or control systems?
It's generally seen as much more flexible, more generalizable, and it scales better to handle real-world complexity. It's a bit like how LLMs can handle almost any text topic subject agnostic. This simulative approach aims for something similar across broader domains.
Like AlphaGo. Did that use a world model?
You could argue it used a very, very simple, specialized one, yeah. It explored the possible futures of the Go board. But what we're talking about now is vastly more ambitious.
Okay, that's the grand vision. Ambitious is right. But let's pull back to today. What's actually being built now? What's the current landscape?
Right, grounding it is important. And when you look at recent efforts, there's a very strong pattern, a big focus on, well, video. Generating images, generating video sequences, and making them look good. High visual fidelity.
Which sounds impressive, but you're saying it might be missing something.
It often misses the broader point, yeah. The focus on just the visuals can be a bit of a distraction from the core goal of reasoning.
So let's look at some examples. Gaming world models, like Genie 2, Muse, Oasis.
Yeah, those systems can simulate game environments, which is cool, for sure, but they're very specific, tied to certain game types, console inputs, maybe just Minecraft.
And they have limits.
Big limits. One key thing is temporal coherence. They can maybe simulate a minute or two of gameplay, not hours. So they lack that long-term understanding needed for complex open-ended tasks. They're not general.
Okay, what about 3D scene models? World Labs.
Those are more about generating static, stylized 3D environments. They can look great, like digital dioramas, but typically there are no dynamic agents moving around, no real physics simulation, not much interaction.
So not really a world in the sense of things happening and changing dynamically.
Exactly. They're incomplete if your goal is decision-making within that world. You need things to react.
Then there are physical world models, autonomous driving, robotics, GIA2, NVIDIA Cosmos.
Right, and these are genuinely impressive in simulating low-level physics and sensor runner control for things like driving or robot arms. High fidelity there. But they're usually very tightly coupled to that specific domain. Driving simulators, no. Driving physics. Robot simulators, no. Robot dynamics. They don't easily generalize to simulating, say, social interactions or abstract planning. They often rely on task-specific sensors, too.
Okay, and then the big ones, the video generation models. Sora, VO, they look amazing.
Visually stunning, absolutely. Yeah. They generate incredibly realistic videos from text prompts.
But they aren't world models. Why not?
Because they only generate fixed trajectories. You give them a prompt, they make a video. There's no concept of state or action or control within the simulation. You can't ask, okay, what if the car turned left instead? You can't use them to reason about different choices.
So they're just video makers?
Fundamentally, yes. Strict video generation tools. Powerful for content creation, but not designed as sandboxes for reasoning or planning. That's a key distinction.
What about the JIPA family? VJPA, Dino WM from Meta. They sound different, predicting latent embeddings, not pixels.
Conceptually, it's elegant. Instead of generating the whole video, predict the underlying representation, the embedding of the next frame. It works in this compressed hidden space, which could be more efficient.
But does it work in practice?
That's the question. The paper notes there's actually scarce evidence they're useful, beyond quite simple toy environments. It's not clear if this approach can scale to complex, real-world tasks, like, making breakfast or planning that mountain climb.
So summing up the current state, lots of focus on video.
Yeah, and the paper argues this focus lacks a compelling justification for what a world model should be doing. The core purpose, remember, is to be a sandbox for reasoning and thought experiment.
Not just a fancy video generator.
Exactly. That visual output might be one useful aspect, but it shouldn't be the sole focus or even the main one if the goal is intelligence.
Right, that makes sense. Which leads us perfectly into the big debates. There's this vocal school of thought, the paper mentions, with 5 specific claims about building WMs.
Yeah, they have a distinct viewpoint and even propose their own alternative framework. Let's unpack their claims and the counter-arguments. It gets really interesting here.
Okay, claim 1. Sensory inputs, video, audio, smell, are better than text because there's just so much more of it.
That's their argument. They point to, the sheer volume of visual data a 4-year-old sees compared to all the text an LLM trains on. More data equals better model, essentially.
Seems plausible on the surface. What's the pushback?
The pushback is about information density, not just raw volume. Sure, sensory data is huge, but a lot is redundant. Low semantic content. Think of hours of security footage versus a single page summarizing the key events.
So text is more compressed.
Exactly. The paper calls natural language an evolved compression of human experiences. It's packed with abstract concepts, reasoning. Text captures things like justice or motivation, things with no direct visual or auditory form.
Things you can't just see.
Right. And text connects us to collective human knowledge, science, history, mistakes made. Models trained on text can write code, solve complex math problems. Visual models are good at navigation, manipulation, different strengths.
So the takeaway isn't video or text, but
both. And likely other modalities too. A truly general WM needs all layers of experience. Over-relying on just one, like video, creates a fundamental bias. You need the whole picture, the concepts, and the sensory grounding.
Okay, claim 2. Representation. They say world state should be continuous embeddings for gradient optimization, not discrete tokens like LLMs use.
Yeah, this hits on a core debate. Continuous versus discrete. Smooth signals versus distinct categories. How do we, humans, think? The paper admits, honestly, we don't know for sure.
they argue discrete tokens are actually an asset. How so? That seems backward for modern AI.
The argument is that continuous inputs can be brittle, sensitive to noise. A tiny change might throw things off. Human cognition seems to categorize raw perception into discrete concepts. Language, symbols, structured thoughts. We don't perceive infinite shades of gray. We see gray car, dark cloud.
So turning things into words or symbols isn't a bug, it's a feature.
That's the idea. Vocabulary-based tokens are thus not a liability, but an asset. They provide a stable, composable way to represent things. It's the foundation of LLMs, and maybe cognition too.
And there's a theoretical bit here about scaling.
Yes, the scaling out idea.
Yeah.
Theorem 1 in the paper. It shows discrete representations can capture fine detail. You don't necessarily need infinite precision in the signal itself. You have two options to scale. Scaling up, making your vocabulary exponentially bigger, which is unsustainable,
Right.
or scaling out using longer sequences of existing tokens, like using more words to describe something complex. This is much more manageable computationally. It's how LLMs achieve nuance.
Fascinating. So the ideal is maybe a mix.
That's the proposal. Mixed representations, discrete tokens for robust symbolic reasoning, continuous embeddings for that fine-grained sensory stuff. Get the best of both.
Okay, third critique. Autoregressive models like LLMs are bad. They're guaranteed to make mistakes, can't handle uncertainty.
That's the claim. But the paper points out a bit of irony. The alternative framework they propose, JPA, is also fundamentally autoregressive and generative, functionally. It predicts the next step based on the previous one. And its deterministic nature doesn't actually model uncertainty either.
What about the error accumulation problem, if mistakes build up over time in simulation?
That's a real challenge in any chaotic system, sure. Errors will accumulate. But the argument is that well-structured autoregressive models can still learn useful abstract patterns. They might not predict every raindrop perfectly a week from now, but they can predict it's likely to rain. They can capture the gist.
And what's the issue with encoder-only models like JPA that don't generate an output you can see?
The problem is diagnosis. If you only supervise the model based on its internal latent representation, without making it generate something observable like an image or text, it's difficult to diagnose whether the model is learning meaningful dynamics or collapsing to trivial solutions.
How do you know it's not just cheating internally?
Exactly. You lose that grounding in reality.
Yeah.
Which leads to the proposed solution.
The generative latent prediction, GLP architecture.
Yes. It uses hierarchical abstraction, multiple layers of prediction.
How does that work?
At the bottom, maybe latent diffusion models handle the noisy, fine-grained, continuous stuff, like pixels or audio, capturing stochasticity.
Okay.
In the middle, maybe a transformer decoder works with discrete tokens, like from a VQ, VAE, handling symbolic structure.
That's a top.
An LLM, operating in a more abstract thought space, doing long-horizon planning, mental simulation, counterfactuals.
So GLP tries to combine structured reasoning and detailed generation.
That's the goal. Mitigate error buildup, allow flexible mixing of discrete and continuous, and keep things grounded.
Makes sense.
Yeah.
Okay, critique 4, the learning objective. They prefer learning in latent space, not reconstructing the actual data, to avoid complexity.
Right. They argue against probabilistic data reconstruction, trying to predict the next frame's pixels, because it's hard and might predict irrelevant details. They favor learning purely based on those internal latent embeddings.
But you mentioned a collapse problem with that.
Yes, Proposition 1 in the paper. If you only judge the model on its internal state, it can find a cheat configuration. It might learn to just map everything to the same constant internal vector. That minimizes the latent loss perfectly. but the model learns absolutely nothing useful about the world's dynamics.
It satisfies the internal check without understanding reality.
Precisely. In contrast, generative reconstruction loss, making the model actually generate the next observation, the pixels, the sound, forces it to ground its understanding. Proposition 2 argues this avoids the collapse.
Is there theory behind this too?
Theorem 2. It shows that the latent loss is basically an upper-bounded surrogate for the generative loss. Minimizing the latent loss doesn't guarantee the model is consistent with observable data. And consistency with data is pretty crucial if you want to model the world.
So the takeaway is, don't abandon pixel space.
Or whatever the observable data is.
Yeah.
Learning from that sensory reality provides a richer and more stable learning signal. It forces meaningful representation learning.
Okay, final debate point. Usage. Model predictive control, MPC, versus reinforcement learning, RL. The vocal school favors MPC.
They do, often citing reasons like needing fewer trials, potentially being safer, learning from offline data. And MPC can work well in some contexts.
But it has downsides.
Big ones in practice. High computational overhead is one. MPC often needs to run many simulations at inference time every time it needs to decide an action. This can be slow. It also tends to have limited foresight, only planning a few steps ahead effectively.
And it struggles with complex tasks.
Yeah, it's hard to scale beyond relatively simplified settings like Go to really messy real-world problems like, say, customer service or navigating a busy street.
How does RL with the world model compare?
RL is presented as more general, flexible, and scalable. The key difference is shifting the computational load. You use the world model heavily during training to learn a good policy network offline.
So the thinking happens beforehand?
Yeah, a lot of it, yes. This allows for fast action selection during deployment because the policy network already encodes good strategies. It doesn't need to re-simulate constantly.
So RL focuses more on long-term strategy.
Exactly. RL optimizes for long-term cumulative rewards, encouraging more strategic reasoning over extended time horizons. The idea is that agents should both reason with and learn from the worlds that they simulate, and RL provides a powerful framework for that learning part.
Okay, so we've dissected the critiques.
Yeah.
Where does this lead? The paper proposes its own model.
It does. It's the combination of addressing those 5 points. They introduce PAN, a physical, agentic, and nested world model.
PAN. And it's designed based on the principles we just discussed.
Precisely. Mixed representation, generative objectives, integration with learning like RL, hierarchical structure. It tries to incorporate those counter-arguments.
What makes PAN different? What's its motivation?
The motivation is key. It's designed with a truly complex, realistic scenario in mind. A mountaineering expedition.
Not a toy problem?
Definitely not. Think about mountaineering. Multimodal inputs, vision, sound, wind chill, muscle strain, maybe pain. Decisions at multiple levels, gear choice, overall route, specific handhold, social coordination with a team. It's miles away from just predicting the next frame in a video game.
That level of complexity demands a different kind of model. How is PAN structured?
It starts with a sensory encoder. This takes all that multimodal input and processes it using both discrete tokens, mapping raw signals up through concepts to words, and continuous embeddings for the low-level nuance. That mixed representation principle.
Okay, gets the input handled, then the core.
The world model backbone. This predicts the next state. It uses an enhanced LLM at its core for the high-level conceptual reasoning, generalization, even dynamically adding new vocabulary. But critically, it also has a diffusion-based next latent embedding predictor for the fast, low-level, maybe subconscious stuff, like quickly assessing if a foothold feels secure, that immediate fiscal intuition.
And it combines these.
Yeah, with a learned switch. It adaptively figures out how much to rely on the high-level LLM versus the low-level predictor, depending on the situation. It lets PAN scale across spatiotemporal scopes and action granularities, zoom in, zoom out.
And it generates output.
Yes, using a multimodal decoder. But crucially, it doesn't just output a video. It aims to reconstruct the full sensory experience. Sound, temperature, motion, maybe pain signals, text descriptions.
Why is that full reconstruction so important?
It grounds the model. It ensures the internal predictions match up with a rich, observable reality. This avoids that collapse problem and makes sure the learning is meaningful.
How do you train something like this? Sounds complicated.
They propose a divide-and-conquer approach. Pre-train the parts the LM on text, diffusion models on video audio, then fine-tune and integrate them using multimodal data.
Is it data hungry?
Maybe less than you'd think. Because of the multi-scale approach, it doesn't need data capturing all complexity simultaneously. Navigation might use coarse visual data, But climbing needs fine foot placement data. Social interaction needs language. You combine different data sources.
And this leads to better generalization.
That's the hope. Cross-modal generalization. Sensory data gets context from the LLM. Abstract LLM knowledge gets grounded in concrete experience, like how we learn, leads to better common sense understanding.
So PAN isn't just a simulator, it's designed to fit into an agent.
Exactly. That's the agentic part. Figure 11 in the paper shows how a PAN agent would work. It uses the PAN-WM for simulative reasoning.
How does that reasoning work? Does it simulate constantly like MPC?
No, it's smarter. The agent can use the PAN-WM offline to pre-compute and cache lots of possible future states, actions, and outcomes based on its goals.
Like building a mental map of possibilities beforehand.
Kind of, yeah. Then, when it's time to actually act, it consults this cache. It looks at its current situation, checks its cache simulations, and picks the action that seems best based on expected rewards.
So it decouples the heavy simulation part from the real-time decision.
Exactly. Decoupling of simulation from action selection. This allows for more deliberate, adaptive, and selectively reasoning. It's not rigidly reactive like some RL, and not computationally swamped like constant MPC rollout.
It sounds more human-like.
The paper suggests it mirrors human-like cognition, planning, considering options, acting thoughtfully but also efficiently.
So this PAN framework, it's a step towards
What?
richer AI agents.
Towards agents capable not just of simulating futures, but of choosing among those imagined futures with intent, moving towards that adaptability, resilience, and autonomy we see in human intelligence.
It's really about purposeful reasoning then.
Absolutely. That's the core message, really. World models aren't ultimately about generating pretty videos or immersive VR for fun. They're about simulating all possibilities in the real world to enable purposeful reasoning.
And the current approaches, the video-focused ones, are maybe just scratching the surface.
They're important steps,
Yeah.
but maybe just the beginning. Frameworks like PAN are pushing towards that deeper goal.
Wow. Okay, what a journey through this field. So, as we wrap up, a final thought for you, the listener. If these AI systems, these world models, truly get good at simulating all possible futures,
And not just simulating, but evaluating and choosing the best path forward.
what does that mean for us? What fundamental questions does it raise about our own decisions, our ability to foresee things, maybe even our concept of free will? If an AI can map out all the consequences, how does that change how we think about navigating our own complex, uncertain lives? Something to definitely mull over.